Hey everybody, it's Miss Smith. So today yesterday we talked about 2D structures and how to draw those. Today we are talking about 3D structures and what compounds look like, what they really look like underneath a microscope. Now, I'm going to give you some notes today that are very, very important that you write down. You will be allowed to use these on your exam, and just based off of this chart that we're going to make today, you will be able to answer several questions on your exam just based off this chart. So please make sure that you write this down. It is extremely important. It is reference material that you will have to go back to over and over and over, so write it down. All right, let's go into the notebook. These are called valence shell electron pair repulsion model. All right, so this is abbreviated valence shell electron pair repulsion. Okay, so these are VSEPR structures. I call it VSEPR. It's actually a VSEPR or something like that, whatever, I just call it VSEPR. Anyway, so let's talk about this for just a minute. So there's important concepts I want to talk about. Now, electron. We know that electrons are negative, okay? So that becomes important in just a minute. Now, repulsion is the other, and this should say shell. Oh, my words are all messed up today. So this say shell, valence shell. So remember, the shell is the orbits that the electrons orbit. So here's your nucleus, here's, shell number 1, shell number 2, on and on and on. You got, electrons out here like this. These are shells. These things are shells. These are shells. So the valence shell is the last one on the very outside where we find the valence electrons. So it's the valence shell electron pair, because remember, electrons like to be in pairs, repulsion model. Now, if you were talking about a magnet, like if you had a magnet like this, and you had a north side and a south side, and you put another magnet over here that was the south side of a magnet, you know that when you try to put two magnets together, they're going to repel one another. It's the same kind of concept, okay? So what happens when, let's say that you have this here. Let me go ahead and put, let's try this. This is one that we talked about yesterday, or something similar. Okay, so I've got a carbon in the middle and 4 hydrogens. Now the question is, why are these out here like this? Why are they all 90 degrees like this? Why is that? Okay, why can't I have them like all bunched up on the same side? Okay, it's because they repel one another. Now, what we drew yesterday, these are Lewis structures. Now, these are 2D, so this is just basic what you can draw on paper. This is not really what it looks like. Okay, so let me draw what it really looks like. So I'm going to use dots to, so I'm going to make this circle, this filled in dot. I want to make that one carbon. So there's my carbon there. And then I'm going to have the ones that are not filled in be hydrogen. So this one right here is actually in the back. Like if I could draw it going out of the paper, well, for you it's out of the computer screen, then I would, but I can't. All right, so this is what it looks like. So I've got a kind of a 3D structure here. So I got one that's going upward, and then I've got 3 downward. This is the 3D structure. This is what it really looks like under the microscope. All right, now there's a name for that one. There's a whole bunch of other ones that we'll talk about. This is the same one. This is another tetrahedral, just looks a little bit different. There's one like this. There's one like this, stuff like this, okay? So we're gonna go into all the different kinds that there are. This is gonna end up being a reference sheet for you, so please make sure you write this down. The reason why these are spaced the way that they are is because these have electrons in them. These are negative. This is negative. This is negative. This is negative. When you put two negatives together, they repel one another. So these are as far apart as they can be because they're being repelled. But it's also repelled by this one. It's also repelled by this one. It's also repelled by that one. So where they are is where they stay because they're being repelled all over the place, which is why this is called valence shell electron pair repulsion model. That's why it's called that. All right, but let's make this chart one. Okay. So the first shape that we're going to talk about, and I'm going to zoom in to do this, the first shape that we're going to talk about is called linear. And so the example that I like to give is BeCl2. Now, just drawing a brief, let's do a brief drawing of what this looks like. We know that beryllium goes in the middle, and I have a chlorine on one side and a chlorine on the other. If you completed this, it would look something like this. Beryllium is a weird one that does not meet the octet rule because it only has 2 electrons, valence electrons, so it can only ever have 2 bonds. Okay, that's the exception to the octet rule. But here, this is the correct drawing for it. Now, if you look at what that looks like, it looks linear. Linear means 180 degrees if you talk about it in terms of geometry. It has 0 lone pairs. Okay, its angle is 180 degrees. And the drawing looks like this. Very simple. 180 degrees, just like that. Looks like this. This is in 3D form. All right, on to the next one. Oh, lone pairs. Basically, these here that are not connected to anything, these here that are not connected to anything, those are lone pairs. Okay, moving on. So this one has no lone pairs on the center atom. That's the question, is on the center atom. How many lone pairs are on the center atom? All right, next. We've got bent. What's the next one on the list? All right, so a great example of bent is going to be water, H2O. Now it has 2 lone pairs on its center atom, and it is around 120 degrees. Now that little squiggly line means about. So let me draw this real quick for you. So I have an oxygen in the center and 2 hydrogens. If you did the math with this, hydrogen is 1 valence electron, but there's 2 of those, so it's 2. Oxygen is 6 times 1 is 6. 2 plus 6 is 8, divided by 2 is 4 dashes. Well, if I just draw the basic skeletal structure, I have, you know, 1 dash here, 1 dash here. And if you remember, hydrogen can only ever have 1 dash. So I can't put them around like this. I can't do that. Okay, hydrogen only ever has 1 electron ever, so it can't have more than 1 dash at all. So the rest of the dashes then go around oxygen, like that. Now I do have 2 lone pairs on my center atom. This is a lone pair, that's a lone pair. And so that's where that 2 came from. That's about 120 degrees. And to draw this in a 3D structure, it's going to look like this. You have your center atom. You have this down here like this. And I have these huge, like rabbit ear things. And this is where those 2 lone pairs are. Remember, 1 dash is 2 dots. So here's the little dots for the lone pair. And because the reason why it looks like this is because, remember, this has like 1 electron here. This is 1 electron here. These are 2 electrons that are not paired at all. So they have a huge amount of repulsion power. So that's the reason why these are kind of pointed downward and it's not flat like linear is. These are pointed downward because this is pushing down because this has so much repulsion power. The version for this one, for bent, looks like this. It has those 2 lone pairs at the top. This is bent. The next one is trigonal planar. Okay, now planar in geometry means flat. So the example for trigonal planar is AlCl3. Now this is a special case, just like it was with beryllium. Beryllium only has 2 valence electrons. Aluminum only has 3. So aluminum's only going to have 3 pairs coming off of it. And if you did the math, you would know that there would be 12 dashes, I think, and you leave it like that. And so this has 0 lone pairs on its center atom. It is all 120 degrees from each other to the next closest atom. When I give you these degrees, I'm talking about the angle between the atoms. This is 120 degrees. This is 120 degrees. Really, this is 120 degrees. But I remember I drew that in a Lewis structure. When I draw it in my VSEPR structure, it looks like this. That's more of what it looks like. We're doing trigonal planar, which looks like, now planar means flat. Trigonal planar looks like this. This one's got a little bent. But this is trigonal planar. It's completely flat. Okay, there's nothing going up or down. That's trigonal planar. Okay, next on the list. Okay, next on the list is going to be tetrahedral. Okay, so a great example of this one is going to be CH4, carbon in the middle, hydrogen, 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 hydrogen. Lone pairs on the center atom is 0. The angle is 109.4 degrees. And it looks like this. Like that. Okay, next on the list. And I've already showed you tetrahedral, the tetrahedral model I showed you earlier. So in the interest of time, I'm going to skip showing you that 3D model. Next on the list is, this is where it starts to get a little iffy, where people start getting a little confused. Trigonal pyramidal. There's the only one that's like this. This one has a lone pair on the center atom. So the great example of this one would be NH3, nitrogen in the middle, hydrogen, hydrogen, hydrogen. If you do the math, you need 4 dashes. Well, you know, I said earlier that hydrogen can only ever have 1 dash, so I can't put any other dashes on hydrogen because it's already here. So my 4th dash that I need needs to go on top like that. Well, I have a lone pair on my center atom. I have 1. So there's only 1 that has a single lone pair, and that's trigonal pyramidal. The angle is 107.3 degrees, and it looks like, when we have a lone pair on that center atom, remember it looks like a big old rabbit ear, but this one only gets 1. So the next one on the list is trigonal. Oh, you cannot read that. Sorry. Trigonal bipyramidal. Trigonal bipyramidal. All right, great example of this one is NBBr5. All right, now NB is niobium. All you need to know is niobium has 5 valence electrons. Niobium in the middle, bromine, 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 and another bromine. And then you just box everything in. You would have to do the math for this, but you just box everything in. Looks like that. Now, this niobium in the middle is which is called a expanded octet. These up here that had only like 3 things bonding off, well, not this one in particular. This one where it only had 3 things bonding off, and this one we had 2 bonding off, that's called a sub-octet. So it's below the octet rule. But what happens if you have one that's above the octet rule that has more than 4 dashes? This is called an expanded octet. Now normally you're going to see an expanded octet with like sulfur or, not sulfur, nitrogen, phosphorus, arsenic, things like that. Maybe sometimes you'll see it with sulfur. So there's a great one that sulfur likes to bind to fluorine. Anyway, this has 0 lone pairs on the center atom. Its angle is 90 and 120, and I'll show you that one in a second, why it is the way that it is. Okay, so the drawing here, so I have 1 up and 1 down, and then I have 3 in the middle. So I have 1 up, 1 down, and 3 in the middle. This is trigonal bipyramidal. Now you're like, wait a minute, Miss Smith, why is it called bipyramidal? Okay, if I took and like made these sides and like put pieces of paper on the sides like this, then it would actually be two pyramids. It'd be a pyramid on the top and a pyramid on the bottom. Like if I'd made a side like this and went all the way around and put like pieces of paper on the side, it would be two different pyramids on top of each other. Okay, last one. Now this is the most complicated one. Oh, I forgot to show you about the angles. I forgot. Okay, so I said that trigonal bipyramidal has two different types of angles, okay? So if you look at the angle between one of these top ones and one of these side ones, this is a total, that's 90 degrees right there. But if you turn it and you look at these middle ones in between here and here, that is 120 degrees there. All right. So octahedral, a great example of this one would be SF6. This is another expanded octet because it has 6 fluorines coming off of it. Sulfur in the middle. Box everything in. Okay. 0 lone pairs on that center atom. Everything is 90 degrees from each other. And this one has 1 in the middle, 1 up, 1 down, and 4 coming off that center atom. That's the most complicated that it gets. Now, that one has 6 elements on the outside, but yet it's called octahedral because if you were to put, like we put sides on the other one, this is octahedral. If you put sides like all the way around, like this, like all the way around, then it would have 8 sides. So it's got 8, basically it's got 8 interfaces. So like this is an interface and that's another one and this is another one. There's 8 of them. So that's where the 8 comes from. All right. So the next thing that you need to know is if you are given a compound, how to tell which one it is. Okay, so let's say that you were giving something like this here, CCl4. Put your carbon in the middle, chlorine, 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 and chlorine. Well, I don't have any lone pairs on my center atom, so I can go ahead and eliminate 2 of them. So this one's out, trigonal pyramidal is out, and bent is out because those have lone pairs. So, but I do have 4 things coming off my center atom. So let me go see if I've got 4 things coming off my center atom. This one has 6, this one has 5, this one has 3, this one has 4. That's the one, okay? This is tetrahedral, all right? Okay, so you have to draw the Lewis structure to figure out what it is. Now let's say, I'm trying to think of some other examples off the top of my head. Let's say CO2, okay? Well, carbon has 4 valence electrons, but there's 1 of them, so that's 4. Oxygen has 6 valence electrons, but there's 2, so that's 12. 4 plus 12 is 16, divided by 2 is 8. Okay, so I need 8 dashes. Okay, carbon goes in the middle because it's least electronegative. And I'm going to go ahead and connect my 2 oxygens. And so I need 8 total dashes. I've already got 2 put down. If I do this, that is incorrect, okay, because that center atom does not have all of the dashes that it needs. Carbon is one that does meet the octet rule. So, because it's got 4 electrons, so it needs a maximum of 4 dashes. So what I'm going to do is I'm going to double bond both of these and they look like this. Now, I know yesterday I didn't talk about putting these at an angle. It's fine. If you don't do that, it's fine. But the point is you've got 2 double bonds. Now this is straight across. There's only one that did that. There's no lone pairs on the center. If this was straight across and there was a lone pair here or here, that would be bent. But there are no lone pairs. There's 2 double bonds. So this is linear. All right, let's try another one. What if I had PCl5? Well, phosphorus goes in the middle, chlorine, 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 chlorine. chlorine. Okay, well, I got 5 things coming off that center atom. I don't even have to finish drawing the rest of this thing. There's only one that has 5 things coming off that center atom, and that's trigonal bipyramidal. There's only one. Trigonal. All right, so hopefully, if you got this, if you didn't get it, let me know. You know where to find me. Ask me questions. I'm here to help.